Let's discuss how we draw coexistence boundaries. In other words, let's discuss the physical basis of a pressure-temperature phase diagram. The chemical potential depends on pressure and temperature, as we've said. And when the chemical potential of two phases are equal, then they're in equilibrium. So let's take two phases, alpha and beta, and at equilibrium, their chemical potentials are equal. If we change the system a little bit, perturb it somehow, but keep those chemical potentials the same, then we would keep the system at equilibrium. We know how Gibbs energy changes with changes in pressure and temperature. It's just given by the fundamental equation. If we divide through by n, then we get how the chemical potential depends on changes in pressure and temperature as well. Now let's apply this to our two phases. We'll substitute in for phase alpha, for phase beta from the fundamental equation. Let's move all of the entropy terms to one side, all of the volume terms to the other, and then make this derivative of the pressure with respect to temperature. That's going to define one of these phase boundaries here, right? And that's known as the Clapeyron equation. When we put it in this form, dp dt is equal to, the change in molar entropy divided by the change in molar volume for that phase transition. Now, what the Clapeyron equation is telling us, right? It's valid for the equilibrium between any two phases. It's valid along that coexistence boundary. It tells us where the coexistence boundary is, right? It predicts then the response of freezing points and melting points to changes in pressure. So let's take a phase transition that's occurring at constant temperature and pressure, right? And we know that at constant pressure, the heat evolved is equal to the enthalpy change. Therefore, we can use that to substitute in here for the entropy, right? Because delta S is just delta H of the transition divided by the temperature at which it's occurring. And so we'll substitute that into the Clapeyron equation, and we'll get this expression here that tells us how the pressure changes with respect to temperature along the coexistence boundary. Now, normally we would get behavior like this, right? Delta H for a transition is always positive, and normally delta V is also positive. So most materials, like aluminum here, right, they expand upon melting. They contract upon freezing, and therefore you have a delta V that is positive at the transition and a positive slope here. Water, of course, has to be different because water is the most complex liquid. It's also the most important liquid, but it's the most complex because of its collective behavior. And that tetrahedral bonding that is going on in there with all the hydrogen bonding. Water, as we've seen earlier, it expands upon freezing. Therefore, delta V is negative, and if you like, the phase boundary has the wrong slope. This has practical implications. There are a few other materials that do this too. Silicon is one of those materials that expands upon freezing, and it can lead to some strange behavior. One is that ice cubes float on water. Solid cubes of silicon would also float on molten silicon, or it can lead to other strange behavior. The one we saw back with a graduate student of mine, then at that time graduate student David Mills, and I were doing laser ablation of silicon pillars, and we found these little spicules that could form on the end of them, little nanostructures, microstructures that form because of a process that is related to this expansion that occurs when silicon freezes, that leads to a pressure jet of liquid silicon that would shoot out from the molten pillar here and then refreeze in this small structure. Hopefully now you have a better idea of how we draw the coexistence boundaries that make up phase diagrams.